Puzzles 2017.
Okay, so we're going to talk about pattern matching and pattern matching within binaries. And the patterns that we're going to define are graphs. So we will see how we can write patterns as graphs and match them within binaries. Just a quick word about ourselves. So I am Aurélien Thierry. I'm a malware analyst at Airbus.
And I'm Jonathan Thieleux. I'm also a malware analyst, but at Storm Shield.
So through our presentation, we will talk about a malware sample, which is Backspace. Actually, that's more like a malware family. It was first seen in 2015, and it's a rat. So what we found in what we find in Backspace is small decryption functions that will decrypt encrypted configuration variables, such as CNCs, ports, or registry entries. So what we see is that the decryption function is quite simple. So it's a small routine. Here we can see it on the left. So you have simply a loop with a XOR which has as an argument 11, then followed with a sub that has as argument 25. In the Backspace family, we find many variants of this decryption sample. So with this kind of family, what we want to do is first to do detection, so to detect the malwares, then to classify the variants based on the decryption algorithm that is used, and then to be able to decrypt the configuration variables since we know which algorithm is being used. One thing you can use to do that is to use YARA. YARA, it works on bytes, so you will write regular expressions on bytes, and so it will look like the following expression. You will say, in order to detect the XOR with then the sub, you will say, okay, I need the byte 80, then I need any byte, you can take any byte, then I need the byte 11, which is the argument here of the XOR, 11, then I need the byte 80, then any byte, then the byte 25, which is the argument of sub. But this way of writing a matching a signature is not really easy to read. So what we wanted to do with GRAP was to have signatures that are based on the instructions that are within the binary and how they are linked to each other. So the kind of signature that we want to do is to say, for this sample, we want to say, okay, now find me a XOR that has as argument 2 11, and it is directly followed with a sub that has as argument 2 25. I'll present a quick overview of the GRAP project. So since we're working on graphs, we use the dot language to represent the graphs. That is simple text files that we will see a lot of examples later, but it's quite simple to write the graphs in this language. And GRAP is at the same time a standalone tool that you can use on the command line. Then it has Python bindings to leverage the algorithms from GRAP from Python, and we also developed an IDA plugin. So everything is open source and available online. So GRAP has two main components. The first one is a disassembler that will take binaries and give you a dot file that is a graph representing the binary. So it's coded with Python and it's based on Capstone. And the other part of GRAP is a graph matching library that can parse dot files and then can do the graph matching. This part is more coded in C and C++. So a typical workflow for our analysis with GRAP will be to write patterns. So that's what we have here, pattern dot dot. So you will write a pattern for Backspace. Then you want to analyze backspace.exe. So you give it to the disassembler that will give you a pattern backspace.dot, which is the disassembled part as a graph. And then you will give the pattern and the disassembled graph to the graph matching library that will give you matches and extract the instructions that you were interested in.
So Backspace is a binary, okay? So it's a sequence of bytes. Those bytes can be interpreted in assembly language, so a sequence of instructions. So we can see the XOR and the subroutine for the decryption. Then we can create a graph, a CFG, so it's the flow of the execution of the instruction. And in the standalone pool, we use recursive function to create this graph, and we are best for the disassembler on Capstone. But for the IDA plugin, we use the IDA engine for the graph. So we can create the graph. At the right, we have, sorry, my French word. We have the graph of backspace, okay, at the right. And we want to match the pattern at the left, which is the decryption routine. To do so, we use we can use the usual algorithm. So at the left, we have the pattern, and at the right, we have the test graph. And the goal is just to search the first call. So, okay, we found the first call. Then we got to look to the children. There is an add, so we got to look to the right. We have the XOR, so we got to try the other child. So we have the push. So we got to search for another call. So, okay, we match a call. The same thing, we have a head, so we go to look to the push at the right children. And no, so we try the other one. Yeah, we match the add. So again, there is a comp. Yeah, there is a compare. Okay. So next, and so on. So we found the push. Okay. And so on. So, okay. It's pretty simple, but you need to check every child of the node. And it's pretty slow on big graphs.
So since the usual solution is pretty slow on big graphs, we wanted to have a fast resolution, so we wanted to have different algorithms. So one thing we can say about control flow graphs is that they are not any graphs. So the first property they have is that usually when you will disassemble them, you'll see that a node in the control flow graph has at most 2 children. It happens when you have, for instance, a conditional jump. You have one child that will be reached when the condition is fulfilled, and one child that will be reached when the condition is not fulfilled. So that's the first property we have on control flow graphs. Another property is that the children are not symmetrical. Usually you will find that one of the child is directly the following instruction as the next address, and the other child is a remote instruction somewhere else in the program. So we cannot invert them. So we will force that in our graphs, you cannot invert the order of children. So what you need to see now is that once we say that children are ordered in the graphs, the objects we're manipulating are not really graphs anymore, and that will help us have a very fast matching. The other thing we can say about patterns, so I talked about control flow graphs in general, but patterns are specific. As we saw earlier, it's easier to match them from their first node. So we will force that every pattern has a first node. So the first node, it's a root node that from this node, every other node of the graph can be reached. So on the example on the right, that is our pattern for backspace, you have the first node on the top, which is a root node, because from it you can reach every other node. Okay, so with this restriction, we will have fast matching. I'll explain why. So this slide will show you how we can represent a pattern on a different form. So the pattern we have now are what we see on the left. So we have a call, an add, a compare, then a push and a push, and the children are ordered. We have child number 1 and child number 2, and child number 1's here. So there is, with this kind of thing, since we have a root node, which is a call, there is a unique way to number this graph with a depth first search. So that is the following. I take the root node, so it's a call, I number this one 1. Then I take the first child of the call, I get here to the add, I number it 2. Then I take the first child, I number it 3. Then I go back to the call, I will go to the child number 2, number it 4, and go to the child number 1, number it 5. So I can describe it on a text way as this. So it's equivalent to the pattern, and that means, okay, I'm looking for a pattern for a graph, which has as a first node a call, then it has a first child. If you take it, you get to an add. Then I take again the first child. If you take it, you get to a compare. Then you go back to the first, to the node numbered 1, which was the call. So you go back here, and you say, okay, now you take the child number 2, and you get to a push. Then you take the child number 1, and you get to another push. So this representation as a text, this text representation is equivalent to the pattern representation as a graph. So once you have this, the question we need to ask is, can we perform the traversal of the pattern within the test graph? So we saw that the pattern on the left is equivalent to the text representation. I add some color because it's nicer with color. Yes, it is. Okay. So now it's easier. I need to find, the first thing I need to do is to find a root node that would be a call. So I have a candidate on the right here, which is this one. Then I get to the add part. So I need to see here is there a node, a child number 1 that would be an add. So I take the child number 1 here, I get to XOR, so it doesn't match. I have to go back. So I have to find another root node that could be a call. So there is one here. Now I ask, is there a child number 1 that is an add? Yes, I will number this one too, so I get there. Is there a child number 1 that is a compare? Yes, it works. Then, okay, take me back to the node numbered 1, so back to the call, so I get there. I ask, is there a child number 2 that is a push? It works. I say, is there a child number 1 that is a push? It also works. So this gives us a matching for the pattern, from the pattern to the test graph. So that is the algorithm that we will use. So the difference with the previous algorithm is that now that children are ordered, we saw that we know that we're looking for child number 1 or child number 2. So you don't have the exponential factor anymore. You will only have a polynomial time for matching, so it's much faster. Okay, so I will stop with the algorithms now. I will go back to the patterns. So I talked about how we can match them, but now I will say what are patterns, how do they look like. So on the left you have our pattern for backspace, which was a decryption routine. And so we said that patterns, there are dot files with specific fields because we will use like conditions, we will use conditions on opcodes, on arguments of instructions, on the address of the instruction, and so on. So on the right here you have an example of a pattern for backspace that matches exactly the two instructions XOR and sub. So what it says here, so it's a dot file, it's a digraph, that's a dot keyword. Then we have the name of the pattern, so it's decrypt with the XOR and the sub. Then we say it has nodes, it has two nodes. The first node is A, with the condition on the node is, okay, I want to match an instruction that has XOR as its opcode and has as argument number 2, 11. I have another node that is B, and the condition is I want to match an opcode that is sub, and that has as argument number 2, 25. And then the part here specifies the edges, so there is an edge from node A to node B, so it means I have a child from node A that is node B. Okay, a few more things about node options and edge options in our pattern language. So I said that pattern graphs are supposed to have a root node that is a node from which you can reach every other node. So in order to specify this node, you can say at the option root is true. That means this node is a root. You have the cond field that specifies the condition. So we can have a condition on opcodes, for instance. We have the getID flag. GetID means it will tell grep, okay, when you find the match for this node, I'm interested in this match, so I want you to print it, or I want you to keep it aside so I can access it later. Okay, so that's for node options. For child options, for edges options, sorry, we saw that childs are numbered, either 1 or 2, so we have an option to specify on an edge if it's a child number 1 or a child number 2. So the example below is the same pattern as previously, but with every option explicited. So we have still the condition. We have, okay, this node is a root, so that's the first node of the pattern. We're interested in this node, and I want you to mark the node with A, so that's the name of the node. For the node B, I'm interested also in the node, so you have to mark it B. And the child number of the edge was 1, because they are following each other, they are sequential instructions. Okay, so back on conditions. Conditions, we will be able to make conditions on instructions, and there will be conditions on the full string of the instructions, like move EAX something, for instance. We will have a condition on the address, condition on the opcode, on the arguments, so the number of arguments, and the text of the arguments, so these are string fields. We will also have conditions on the number of incoming and the number of outgoing edges. Sorry. So that means the number of fathers and the number of children of a node. I have an example here that says I'm looking for a function that is frequently called, so that there is a call to this node. So the call is a node A, and the instruction being called is B. And then there is an edge between A and B. So the number of the edge is 2 because it's not a following instruction, it is a remote instruction. And the condition we have on node B is that it has multiple incoming nodes, so that will help us find functions that are frequently called in the code. Okay, so until now, I explained how we can match one node to one instruction. But what we will want to do next is to match one node to multiple instructions. Like when you want to match basic blocks, sometimes you don't care how many instructions there is in the basic block. You want to match to say, okay, this node needs to match a whole basic block. So we can specify a minimum number of matches for a node on a maximum number of matches. It only works on sequential instructions within basic blocks. So these are instructions that have one father and one child. So it looks like that. If you have a basic block that we see here in IDA, so there are 2 incoming nodes, 2 outgoing nodes, and only 3 instructions here. To match this kind of things in GRAP, you just have to say, okay, I want you to match any instruction. That's what it means. Cond is true. And then I need you to match 1 or more instructions, so repeat is plus. If I want to match 3 push instructions, I will write something like that, like I want instructions with the opcode push, and I want them to be repeated 3 times. So by default, GRAP will take the most matching instructions when you specify repetitions, but you have an option to change that. You can say lazy repeat is true. So the first point was greedy repeat, like you take the most of them. With lazy repeat, you will stop once the next condition is fulfilled. I'll give an example here. So back to backspace sample, we had a decryption loop. So we're interested especially in the XOR and the sub instructions, but we can say, okay, I want a loop that looks a bit like that. So I will want to match 1 to 5 any instructions. We have 3 here, but maybe there is less, maybe there is more. Then we have the XOR, then we have the sub, then we have again 1 to 5 instructions. Then we have a conditional jump that loops back to the beginning of the loop. So the pattern will look like that. We will have here, that's a dot representation on graphs. 1 to 5 any instruction, then the XOR, the sub. 1 to 5 any instruction, then the conditional jump. In GRAP, it will, the pattern will look like that. You will say, okay, I'm looking for any instruction, repeated at max 5 times, and I want you to stop once the next condition is fulfilled. So it will match for this node A, it will match move, add move. Then here it will stop because the next condition on B is fulfilled because we have a XOR. Then B will match XOR, C will match sub, D will match again many instructions, so inc, compare, move. And it will stop on the last one because the last one, it says that it wants instruction to begin with J and to have 2 children, so that's the case with the conditional jump here. Okay, so back to our backspace samples. So I'm going to do a demo. We have 100 backspace samples. I want to disassemble them. And then I want to detect the decryption algorithm that I saw, that is the one we reversed in IDA. Then I want to find variants of this decryption algorithm. And finally, I will need to detect all the decryption algorithms. So demo time. Okay, so I have my samples here. So 100 samples of backspace. And I have a pattern. So that's the one we saw in the slides. So we have a lazy repeat, we find the XOR here, then the sub. I want to match it against the sample we know. So I ask GRAP to match it against sample this one, so that's the one we worked on. So first it will disassemble the binary, then it learns the pattern, so there is one pattern that was learned. The test graph, which is the sample, has 8,000 nodes, and it found one matching here. So the matching is described here. So we have the instruction that match. We see the XOR and the sub that we were looking for. Okay, so that was for one sample. I want to do it on every sample of backspace to see what happens. Okay, so it will take a while because it needs to disassemble 99 samples. It takes around 20 seconds. So what we will see is a lot of matching and a lot of text, and then I will show you another option to have less verbose output and a more quiet one with one sample per line. So that's what I say. We have a lot of text. So now I'll ask it to do it quietly. So it will be much quicker because we don't have to disassemble the files again. I'll show you that. If I show the folder, now we have the dot files, which are disassembled versions of the binaries. Okay. So now I'll launch it again, but with the quiet option. So here I see all the patterns all the binaries that matched our pattern. But I don't see the one that didn't match. So we find a lot of samples that use the same decryption algorithm, exactly the same, but maybe there are more. So I will ask GRAP to show me all the binaries. So, okay, we see that some samples match and some others didn't match. So what I wanted to do next was to find variance. To find variance, I went back to IDA, which is here. Okay, so here we have the decryption algorithm. I will see how it is called. So what we see is that it's very simple. You have a first basic block, then a loop, then another basic block. I will see how it is called. So there is a function here that has a lot of calls to the decryption algorithm. It's always two pushes because they are the arguments, then a call to the decryption function. So I wanted to write a pattern to see and to detect this. So what I did was this pattern. So I asked that we find something with two pushes, then a call, then again two pushes, another call, 4 times. And they all point to a function that has a first basic block, then a loop, then an end basic block, then a return instruction. And what I say here is that I'm only interested in getting the loop. So I say get ID. I set get ID only on the loop node. So I'll show you how it looks like with dot. And I have a colored version because it's always better with colors. Okay, so we have here 2 pushes, then a call, then 2 pushes, another call. They all point to the same function. And we're interested in the loop here, which is where the decryption algorithm happens. Okay, so now I need to match this against my samples. Okay, so I find here the first decryption algorithm that we already know is the XOR 11 and 25. Again, the same. Here we have another one. There is a sub, then a XOR with another constant, then another sub. Then there is again the same one. Then, well, we will find that there are many more. I won't show you them all, but what we did next was to write a pattern for these decryption variants. So we have, there are very small patterns. So the first one is the one we knew, so 11 and 25. This one is the one we just saw, with B and 12. And there were like 5 other ones that I won't detail. So what we do now is we want to match them against the backspace samples. So what we see here is that a lot more samples matched, and we know which algorithm was used. So here, the pattern that matched was the XOR sub. Here it was a sub XOR sub. Here there is another one, etc. So one more thing we wanted to know is that we still have some unmatched binaries. So, oops. So I want to know why they don't match. Okay. One simple thing we did, not really in this order, but it works. Okay, we asked for section names. We see that it's UPX, so it's some samples seem to be packed with UPX. So what I'll do is I wanted to have a quick signature for these UPX files. So I will look for basic block loops. That means basic blocks that loop to themselves. So I have a pattern for that I will use now. on this pattern. So I find two basic block loop. I didn't really look into what they're doing, but I wanted to use them as signatures. So I wrote a UPX signature, which contains these two loops, UPX loop 1 and UPX loop 2. So what I did next was to match them. Okay, so there seems to be more samples that are packed with UPX, and I always match the two loops. So I know how to detect variants of backspace. I know how to detect files packed with UPX. So I want to detect them both. So I will combine the two signatures. And I will match them. Okay, it's better. So we still have a few unmatched binaries, but most of them, we see that they are either a variant of backspace and we know which algorithm is used, or they are packed with UPX. Okay, back to the slides. So what we saw is that we found 7 variants of UPX. So there was the first one with XOR 11 and sub 25. There was another one that we saw, then 5 other patterns. We also found out that some binaries are packed with UPX, and we wrote a small, a quick signature for these files. We matched them. So what we did is on our 100 backspace samples, it took around 20 seconds to disassemble them. Then to do the matching of 9 patterns, it took a little more than 2 seconds. And in the end, we see that there are like 17 files that are packed with UPX. The half of the samples that have the first pattern that we looked at, and the other patterns are used sometimes. And in the end, there was still 11 binaries that we did not identify correctly.
So, okay, to simplify the creation of scripts, we create Python bindings of the C++ library with Swig. And now with Python, we can disassemble, we can load patterns and test graphs. We can load pattern graphs and test graphs. We can match patterns and parse all the results. So here we have some example of Python scripts. So at the beginning, we have the import of a library. Then we have we load the pattern.file. We extract the graph from the binaries with disassembled file. Then we load the test graph, and after we match the graph, the pattern in the test graph. So here is an example of a pattern. We want to match 3 pushes. So we use the match graph. And now we can get all matching patterns. Then we can select the pushes patterns. And now we can, with these pushes patterns, we can get all matched instructions. Then we can say, okay, I want to get the IDP. So it gives all instruction with the get IDP. And then we select the first instructions. So now we have the instructions, so we can request some information like the addresses, all instruction strings, the opcode, the arguments, and so on. So okay, we can match the decryption loop, and we saw that we have a lot of pushes and call to the decryption strings. So we want to match the 2 pushes and the call to the decryption routine. Okay. So we want to match the first pushes, which is the length, then the encrypted string, and then the call to the entry point of the function to decrypt those strings. So we have the decryption entry point. We can match the address of all the decryption loop. So we have the address of the match. Ah, damn it. Okay. So to get the entry point, we know that the function is very slow, very tiny. So we can say, and we know also that the decryption entry point is before the decryption loop, okay? So we can say we want to search a node between the decryption address and between the decryption address -30, okay? And we want to match a node with at least 5 or more incoming. So a little demo. So the script is here. We have the import, then we get the binaries, we create the graphs. Then we have those patterns to match the entry point, then to match the pushes before the call of the decryption function, and we implement all variants of the decryption algorithm. So here you have sub-XOR, sub-add, and so on. God damn it. So, maybe I have it in my log. Okay, so we go to execute the script with a sample. So now we can decrypt those strings. So we have the sample, we match the decrypt XOR sub, okay? Then we found the address of this routine. Here we match the entry point with the more than 5 or more than 5 incoming between the address of the decryption -30, then the address of the decryption. So we found the decryption function. It's the entry point. So now we got to look for the pushes, okay, with the entry point of the function. And then we match 35 calls to this decryption function. And so after this, we take the string, the encrypted string, then we decrypt it with the algorithm. And now we can see we have some registers and some text files and so on. So now we can do this on all samples. So here we have first samples with strings, registries. Then we can find some exe on other samples, and so on. So there we have all the strings of the configuration and so on of backspace. So, okay, we have a tool, but it can be nice to have a plugin too in IDA to match those patterns. So we have an IDA plugin. We convert the IDA graph for GRAP. Then we can match patterns with pgrap, which is the Python binding. And then we can, with the UI, browse those matches and put some color on it. And then we apply some filters technique. So match a single pattern. For example, for RC4 set key, we have 2 small loops for the initialization. And if we create just one pattern for those 2 loops, we have a lot of false positives. So we create some filter techniques. It's quite simple and obvious. So for example, the set key for RC4, we have 2 loops. For the first loop is the first pattern, and the second loop is the second pattern. So if we don't have those 2 loops in the function, it's not our function. So you can see at the right we have the 2 patterns. So okay, it's accepted. But if we have just one pattern, it's rejected. We have also the rate techniques. So also quite simple. We have 2 loops, but if we have more than 2 loops in the function, so if we match, for example, 3 times the pattern 1, the function is rejected too, because we just want the first loop one time and the second loop one time too. Then we have the threshold. So sometimes with the pattern we can have some errors. So at the right we have 4 patterns for one function. So we match all patterns, so okay, it's good. But in the middle, the pattern number 4, are not here. So the function is also, for example, the function of decryption, but we missed some patterns. So we create a threshold. So here we have a threshold of 0.75. That means that at least we want 3 out of 4 patterns. So in the middle, it's accepted too. But at the left, we just have 2 out of 4. So we reject this function. The last one is the overlapping. So in, for example, again, the RC4 set key, we have the 2 loops. We create one pattern for the first and another for the second. And if we match the same loop with those 2 patterns, that means we match the same loop, and we don't want this. But in the example at the left, we have 2 matches of the first pattern and 1 of the second. There is an overlapping between the first and the second. So if we remove the pattern number 1 for the overlapping, we have valid matches at the right. So we can say, okay, it's our function. This technique is not yet implemented in either GRAP. So the creation of a rule for the plugin is quite simple too. So for the RC4 set key, we create the first loop, so loop 1. We give the path to the dot file, to the pattern. Then we give a name, a description of this pattern. Then we say, okay, a minimum pattern is 1, so that means I want to match 1 time this pattern or more. Then we fix the max pattern, so we say I want at max 1 time this pattern, so we must match just 1 time the first loop. We do the same things for the second loop. Then we create the function patterns, so we give the 2 loops because we must match those two loops in the function set key of RC4. Then we put the threshold that here is 1, so it means we must get the two patterns to validate the function, then a name, a description, and blah, blah, blah. So demo. Okay. Yep. Okay. Yep. Just for. Damn it. Oh, okay. So I'm going to load the plugin. Yep. So the fingerprint is to find the patterns. So okay, we launched. Here we can see we have matched some patterns. So yep. We can click on it, and then we have the decryption routine. Okay, but sometimes we don't know really where are the matched. So we put some color in it. So here, beam. Okay, and then we have the color on the 2 instruction for the decryption loop, and we have some color on the entry point. So, yep, here we have, okay, is the pushes for the strings, and if we, I don't know, we rename it, yep. Okay. Yeah. And then we launch again the scan. Here we have yep, the name of the function also, with the number of instruction and so on. So okay. RC4, the match are not efficient because the loops are very small and very generic. So we still have many false positives, but we have few false negatives, which is cool. So the tooling is appropriate, okay? And we can try maybe to create other signatures for other cryptographic algorithm, packers, and so on. And maybe we can put the filtering techniques in pgrap, because it's only in IDA-grap. So the perspective, some limitation of our tools. All the arguments, instruction, opcode, and so on are in our strings. So sometimes we have to do some dirty hack to get, for example, here the conditional jump. So we want to match an instruction strings that begin with J, okay? And we want the node to have two children, because in the graph, the instruction with children are calls and conditional jumps. So we are lucky calls begin with C, so okay. Then we have other problem, because in the standalone tool we use the Capstone engine, and in IDA we use the IDA engine. So sometimes with, for example, the variables we have in IDA 25H for the hexadecimal value 25, and in Capstone we have OX25. So again, a dirty hack to catch both cases. So R2 we catch 25 or OX25. So the solution is semantics. The idea behind that is to say, okay, I want to check if my argument 1 is a register, or I want to check if the opcode is a conditional jumps, and so on. The same things for arg1 if we want to catch an integers with the value 25, but maybe in GRAP v2, okay?
Okay, there is another limitation of how we write patterns. That is we explain how we can do node repetition, but there is one limitation that is the following. We can either, with node repetition, we can either say I want the least number of matched instructions, or I want the maximum number of matched instructions. There is no in between. So the problem is this one. We have a pattern that says I want to match 1 to 4 any instruction. Then I want to match a XOR, then I want to match a call, then I say, okay, these are our following instructions, so it's 1 to 5 anything, then a XOR, then a call. And so there is a lazy repeat here. We can either put true or false. If we put true, it will mean that we want to take the least number of instructions. If we put false, we want to take the maximum number of instructions. So we will see how to match this pattern on a binary graph that would have a push, then a XOR, then another XOR, then a call. So with the current tool set, if we put lazy repeat to true, the matching for the any node will stop once it reaches a XOR. So for any, it will take push, then it will stop. Then the XOR node will match the XOR. Then the call node will try to match a XOR. It doesn't work, so there is no match. So it doesn't work with lazy repeat at true. If we put lazy repeat at false, so the any node will try to match the maximum number of instructions. So the problem is it is greedy, so the any node will match push, XOR and XOR, because it matches 4 instructions. And then we get to the XOR node that finds a call, so it doesn't match, so it doesn't work either. So there is no way for our tool now to match this binary thing with this pattern. But it is counterintuitive, because as with regular expressions, we would like to say, okay, I don't care if any takes 1, 2, 3, or 4 instructions, I would like to test them all. So of course the solution, maybe also for GRAP v2, would be to try every number of repetitions, so 1, 2, 3, 4. Of course it will be slower, so we will need to watch out for an impact on performance. Okay, we have a lot of more ideas that we would like to implement in the patterns. One thing that is limited also with the current version is that for basic blocks we only have instructions on the condition on basic blocks for now will apply to every node. And what we would like to say is I want find me a basic block that has at least one XOR instruction, or find me a basic block that has at least 2 XOR instructions and 1 compare instruction. That we cannot do for now, so maybe we will also work on that later. So we said that children are numbered. So you have to specify when you do ages if you're talking about child number 1 or child number 2. Sometimes we will want to say, okay, I don't care. So this may be for instance, for a conditional jump, you could say this could be the child for when the condition is fulfilled, or for when the condition is not fulfilled, I don't care. So we would like to add an option that would be child number is a question mark, and so the algorithm should try the both options. Then, as Jonathan explained, we would like to have meta patterns in GRAP, which would be able to, for us to say, okay, I have 5 patterns. I want a match if we find 3 of them. That's enough. Or we would like to say, okay, I have 2 patterns, P1 and P2. Find me a binary that has one match of P1 that is directly followed by a match of P2. That is, there is one instruction of P1 that has, as a child, an instruction of P2. That we would like to do some pattern linking like that. The last point is that for now we constructed graphs manually with writing text files. It works, it's okay. When you have when you're used to it, it's quite fast. But it would still be easier to be able to select nodes in IDA and then click export. It would generate a nice dot file with all the nodes and all the edges that you want. It will be much faster to create patterns. Okay, so this will end our talk. The conclusion is that GRAP is at the same time a standalone tool. It has Python bindings. We have an IDA plugin. Our goal was to create a tool that can make graph patterns that are easy to write and easy to understand. We believe it is useful for detection and automatic analysis. We showed that on Backspace and it works. The tool is fully open source and you can find it online at this address. As perspectives for the future, or maybe for the V2, we would like to add some pattern features. We talked about parsing semantics information from instructions. We talked about condition and basic blocks. We would like to be able to create patterns directly within IDA. And then we would like to have many more examples that work on crypto algorithms. We would want to try with AES and on packers, on command packers. So this will end our talk. Thank you for listening, and we will try to answer questions.
Thank you for the talk. Very good talk. I was wondering if you had thought about using, since you can have Capstone in IDA now, I think. I haven't tried it, but could you just use Capstone everywhere? Have you thought about that?
Sorry, to use Capstone in IDA?
Yeah.
We thought about it, but we have not decided yet how to do.
Another thing to put onto the list, I guess.